Beshbichi. I'm a recent graduate from Politecnico di Milano, and today I'm going to just talk a bit about my research I did during my master thesis at NTNU in Trondheim, Norway. I basically work on ray corrugation development, and more specifically on writing corrugation, as we'll see. Here, just to give okay. Seems like it doesn't work. Okay, just doesn't work. Please show must go on. Yeah, all right. Yeah, here just to give a bit of, introduction. You know everything about it, I'm sure. But ray corrugations are quasi-sinusoidal ray irregularities. There are a lot of types of ray irregularities, and one of the most common ones typically develops on low rails in tight curves, which is the so-called radial corrugation. Why is it actually an issue? It is a problem because it can lead to a high dynamic loading of track components, therefore poor ride comfort and high noise levels. Therefore, we have to do something about it. And the way we do this is through rate grinding. So we remove material after its formation, but it will be better to find a way to prevent the formation of corrugation beforehand. All right, so formation. Here we can look very fastly the formation mechanism for corrugation, which is composed by two components, a wavelength fixing mechanism and a damage mechanism. The wavelength fixing mechanism relates the wavelength of corrugation with the frequency of vibration of the system, while the damage mechanism is the way the material is removed by the system. In order to excite the system, there are actually there are actually a lot of excitation theories, two mainly. The first one is called, considers the longitudinal rail head irregularity as excitation method, while the second one considers the instability of the wheel rail system in particular situations. For example, when the contact forces are near saturation. There are two points of view. The first one is in time domain, which considers the roll slip vibrations. And the second one is in frequency domain, which considers still the extraction of the self-excited vibrations of the system. Since this latter case is actually computationally faster than the other ones, since it's in frequency domain, we have decided to use this one as in our analysis, because we're going to be dealing with parameters analysis, so it's very an effort computationally. This method, here we can see very fastly the logical flow of the analysis, which is called actually complex eigenvalue analysis. We start from the structural linearized equations of motion of the system, where Q is a vector of the external forces, which in this case is just related with the friction forces of the system. If we look at the global stiffness of the system, we can see that the matrix is actually not symmetric, and therefore it can lead to fluttering instabilities. If we go in frequency domain through approximation methods, in this case we have used the subspace approximation method, we can extract the eigenvalues, in this case complex eigenvalues, since we're considering the damping and the friction forces and the eigenvectors of the system in a frequency range of interest, 0, 1000 hertz. After we have gotten the eigenvalues of the system, we can define what is called effective damping ratio, which is a parameter that is used to relate to the system stability. And if this parameter is negative, then that particular mode will be unstable, and therefore it will be related with high amplitude vibrations of the system, and therefore it can be correlated with corrugation formation. All right. Okay. Here, very fastly, the method of this analysis, we focus only on tight curve steady-state conditions. So we're going to just be looking at routing corrugation information. We just, in our finite element model, because we need the equations of motion of the system, we just consider the leading wheel set of the leading bogie of a one-car vehicle. In order to get the steady-state suspension forces at the bearings, we have performed preliminarily an MBS dynamic analysis. The geometries are standard. And we have considered two-wheel transversal profiles. On the left, an S-shaped European, very commonly used in Europe, while on the right, a commonly used transversal profile in China, in the metro lines, actually. All right, this is going to be one of our parameters in the analysis. For what regards the contact interaction in our finite element model, everything is basically standard. We have used as normal contact a penalty method, while the tangential contact is considered through a column friction model with a certain elastic slip. For what regards the rail pad and the ballast modeling, we have used springs and dashpots in an area, so distributed, while the finite element model length has been considered by computing the vertical receptance of the rail at different lengths and considering the convergence of the pin-pin resonance frequency, leading to an acceptable convergence for 11.4 meters. Here, finally, we can see on the top the factors we have considered in our analysis. We have 4 factors, 2 free levels factors, which are the vertical pad stiffness and the vertical ballast stiffness. The values are taken from the Eurobolt project, while the last year, of course, we have the wheel-set transversal profile and the rail gauge. We have a standard one and a widened one. Finally, we can see we have defined, let's say, a corrugation index that takes into account both the instability of the system in particular situations through the effective damping ratios the negative effective damping ratios detected, and the ability of this unstable vibration to generate wear near the contact patch through that slip ratio that considers the difference of the displacements between the wheel and the rail near the contact patch. All right, here we can see the results of the analysis in terms of just one of the cases of our parameters analysis, where we have got instability. On the right up part of the slide, we can look at all the effective damping ratios detected in our frequency range, while on the bottom, we can actually look at just the near-zero effective damping ratios. As we can see, there are 2 negative effective damping ratios, therefore related to unstable vibrations. If we look at or take into account, let's say, the first one, which is the lower frequency one, we can look at the mode shape here on the left. And we can point out that the vibration is almost all related to the low rail side of the system, and the displacement is almost all lateral. The frequency is all, we can say that, we can point out that this is interesting because it's, let's say, related, not related, but we can say that there is an accordance with the literature on routing corrugation. All right. Here, we can see the results in terms of the design experiment or the parameter analysis for what regards the free level factors. On the top, the effect of, we can see the effect of the rail, of the vertical ballast stiffness. And on the bottom, the effect of the vertical pad stiffness. In terms of the main effect and with the solid line and with the other lines, let's say the combination effect of with respect to the wheel-set transversal profiles. All right, so we can say 2 things mainly. That on the top, we can look at let's say, I mean, we can say that there is a maximum of the corrugation index for a medium ballast stiffness. But most interestingly, we can see that there is a minimum of a corrugation index for a soft rail pad stiffness, which is, again, in accordance with the literature, basically. Here, finally, we can see the effect of the rail gauge on the corrugation index and the interaction effect with respect of the rail gauge and the Wilson transversal profile respect on the corrugation index. Here we can see that there is a huge interaction effect between these two parameters. For example, if we take into account the European transversal profile for a standard 1445 millimeters, we don't have any response of our corrugation parameter. While for a widened gauge, 1455 millimeters, we have a huge response. And the opposite can be found for the Chinese transversal profile. The same basically can be seen through Pareto chart effects up to the second order interaction. We can see there is actually a significant interaction effect between these two parameters. So in conclusion, basically, there are two things interesting to point out. First one is that the results of this analysis match well with the corrugation wrapping corrugation experimental evidence. And secondly, as we've seen, that there is a significant influence of on-ray corrugation of the interaction effect between the rail gauge and the Wilson design or the transversal profile, so geometry. And therefore, we can say that taking all the hypotheses of this analysis, we can say that there is a possible inhibition of radial corrugation by means of an optimized coupling between the Wilson design and the rail gauge. That's it. Thank you.
Thank you very much.